So while that's going, it's interesting is University of Washington is kind of a special place for me. So I've been involved in, I started out in hypersonics and single stage to orbit, and I got really excited about computational fluid dynamics back in what, 88, 89, and came out to NASA Ames to do a research project on using supercomputing for parametric simulation and design. And so I've been kind of like interested in using, large scale supercomputing, not for point simulations, but for, exploring the whole mission profile. So around 91, I kind of had this great idea. I was going to go start a software company. So I started this company, and I did a contract. It was called a cooperative development agreement with this one guy at Wright Pat. Was doing a lot of work in space access, single stage to orbit, scramjets, and it was like kind of like that was I was really excited. Anyway, so what we were looking at was a kind of a fully parametric multi-physics modeling environment. It was kind of like a language, and so we did a CRADA that came up with original ideas. And then eventually, I mean, I was 22, right? So, a 22-year-old isn't gonna win an SCIR. I kind of was deluded. So I didn't win it, and then somebody else won it. And I got all mad and I said, okay, I'm gonna go off into the commercial software world. So I went off into distributed supercomputing to try to do this commercially. And so while I'm doing this, John Livingston, the guy that worked on the CRADA with me, he ended up doing like 3 or 4 iterations of that environment, and then it became a part of something called Create Da Vinci. So if you guys ever heard of Create Da Vinci, yeah. So Create Da Vinci is essentially what I'm working on with John. So now John retired, he's working back with me, and the guy that won the SBIR is also working. So this is Dr. AJ Kathari. So this idea of digital twins, as they're called now, it's not a new idea. It's very old. So we're reinventing. AJ did this thing called SIDE, which is what the SBR contract he went on. So I went off and I started looking at distributed systems and very extreme high performance computing. Somehow I got sucked into the feature film and games world. And I spent some time at the very lowest levels of the game consoles, like the PlayStation 2 and 3, which are all highly embedded real-time systems. You'd be surprised. My wife kept on saying, no, you gotta go back to space. That's where you really belong. So, well, yeah, but I spent 30 years scratching this, modeling simulation edge. I gotta get it out of my system. So I started thinking, okay, what could I do? So about a couple of years ago, I said, God, all these crazy startups are doing all these things about space. Like, what happens when something goes wrong? Who's going to go get them? And it's like, are they going to just die up there? So I kind of floated this idea. AJ had done some work with John.
Sorry.
Good. Yep. Yep. You're too quick. So, yeah. So I'll do it real quick. So anyway, so the space rescue thing, we designed a 2-stage to orbit vehicle. We designed a 2-stage to orbit vehicle that was published at SciTech 2024. This is the follow-on to that. So this is in space only, right? So I'm going to run through this fairly quick and then show you a live demo, if this will go. There we go. So real quick, I'm demonstrating this to one of my mentors. He just passed away. I'm going to his memorial tomorrow. This guy was really special to me. He helped me negotiate a license agreement with a company that just came out with the brand new embedded FPGA SoC. I worked on the earlier generation one. And anyways, this whole presentation is for John. Okay, so what are we doing? So it's essentially, there's 3 products that we're developing. I promise this isn't going to be a sales pitch. It's just going to be very technical. It's the modeling environment, a simulation core, and a hardware platform, right? So all of the stuff that we're doing with mission architecture, simulations, they're all use cases, right, for those core 3 pieces. So you'll see elements of those 3 in a second here.
So let's start at the very top level of a real mission scenario, right? So the thing is that if something is imagine a scenario where you have a Starship HLS, it takes off from the moon, it goes into an intercept orbit with the gateway. There's a stuck valve condition. It goes out of the halo orbit. It escapes the moon's gravity well, keeps going, builds up. Now it's on a highly eccentric orbit. What's going on?
Later.
It's on a highly eccentric orbit. So now there's a second vehicle that goes in, has to intercept with it. Now, in order to do it, it's like you've got a certain limited amount of oxygen, so you have to get there really fast. If you use a chemical rocket, you're not going to have the amount of thrust you need. So the option is, what are the options? The option is a nuclear thermal rocket. So Draco's flying in 2 years. What we did was, so I came up with this thing. It was like, okay, AJ's working on a molten salt thorium reactor, right? That's kind of his follow-on after hypersonics, right? So he's been working on that for 5 years. So we took that molten salt reactor and then put it into this mission concept. So the idea was we wanted to have very high thrust. This thing has about, over 2.5 times the thrust of the highest end full, the stage full flow combustion cycle Raptor engine, and it has almost, about 900 ISP. So there's lots of advantages of this for think of it as an orbital tug, right? So if we go down to, I wish this thing would go. There we go. Okay, so here's the mission scenario I just talked about, right? HLS goes on to its lunar departure. It's go.
You gotta talk into the microphone.
So, yep. Next step is it's getting into approaching gateway, stuck valve, keeps going. Then MARV is basically detaches off of it's in gateway. It doesn't have to be. It's just sitting there. It goes up, intercepts the orbit, and then it tugs it back. So that's the scenario. So really quick, I got some last minute sizing updates. So I just wanted to throw this here real quick. So we know that the whole vehicle was actually sized. I did the first sizing on the vehicle, and then John kind of literally resized it and gave it to me this morning. So I wasn't able to put it in all the PowerPoint. So this will be in the final one that I send out to everybody. I'll take the actual correct ISP and mass numbers. So that means the tanks were sized, we sized pretty much the volumes and all of the things that needed to be done, we did. So even though we're doing a lot of stuff with computer graphics, and I've had like many years, and we've built our own renderer and all that stuff, we're also doing a lot of physics models, right? Of the rocket engines, that. So this will be integrated into the presentation, and you guys will be able to see that. But I just wanted to. So the numbers that I have in this particular presentation are the. There we go. Are the old ones. So these are the old numbers. So this is the concept for MARV. And the original numbers I did is I went through, I sized the tanks, got a rough sizing of the nozzles, and then came up with the mass budgets for this. And then once we had that, then I took AJ's work on his thorium molten salt reactor, and then I came up with ISPs for the 3 different things. If you look at the ISPs for us, the updated numbers are in, I'll put in the final presentation, but you can see they're quite high. And then so now the question is, well, aren't you doing Draco? And said, no, this isn't Draco. Why? Because Draco's doing a kind of a fission reactor. This is a thorium molten salt reactor. And the one thing that's really exciting about this, one thing that's really exciting about this is you're looking at a 500 watts to 1,000 megawatt power. Now think about this for a second. This is a side thing, but this is important to think about when things change big, right? Well, if you've got 500 watts to 1,000 megawatts and you want to have computing there, right? I mean, these chips that we're all thinking writing our software on, My God, they're like, what, 10 watts, maybe 100 watts if you look at the new ultra scale, right? You know, if you look at data centers and the compute capability they have, they're like 1.2 kilowatts of device. So all of a sudden you're talking about 10 kilowatt servers, you know, and so if you had a 500 megawatt reactor, what kind of compute you could build in space? So people are talking about data centers, but they're talking about these massive arrays of, you know, of solar panels. It's like a big giant target for something to hit. I think it's kind of crazy. I think if you're going to build some kind of a deeply embedded computing system, you're going to want that thing powered by something that so it's small but super dense. You can't get away from the power. You can lower it, but it's my point of bringing that up. When you have these, and this is like 2 years, they're going to fly the first fission reactor, right? So this is going to change everything. And I think, you know, a lot of times we don't think about it. We just kind of go with what we have without like stepping back. So, well, what could we do? And this is kind of like what the exercise on this is. So just to give you an idea, what's different from Draco? Well, when you use a thorium molten salt reactor, it's not using uranium-232. Good thing is that there's no proliferation risk, right? Second thing is it's very low amounts of radiation. Third thing is it's not under high pressure. So what that means is you're not going to explode this thing, right? It's always in a liquid state. That's why, you know, so there's a lot of benefits in this work. Now, China's already built one. In the US, there's a couple of startup companies doing it. You know, AJ has his own design, and I'm just piggybacking it. So it's all his work, not mine. But I'm just kind of like, I just said, like, well, why don't we put it into a space tub? And that's kind of like the idea. So irrelevant what happens with Gateway, you're still going to need something to go back and forth between Moon to Mars or LEO to Moon. And something like this, I think sooner or later is the future. I have to tell a little secret. I've been stuck in the stupid computing world for 34 years of my life. I never wanted to be there. I wanted to build things like MARV. So the idea was, it's kind of, I'm being sneaky. I'm doing what I really want to do, but there's such a stupid fancy marketing demo. But it's not, it's real because I care about it. So we're going to keep working on MARV as if it was fully funded. Now we're not funded, we're all bootstrapped. All of my guys are phenomenal, but they're like, you know, there's no money, there's no organization, there's no NASA contract, there's no DoD. Of course, I'm trying to get one, but we're just building it. So the idea is like, even for things that are concepts, we're taking it seriously, and I think it's important. So how do you put this up there? Well, so I did a quick look into how I could assume Starship. I mean, they keep going, they actually succeed with 100 tons. Now we can assemble this in space, you know, in about 6 or so missions. So it is a big vehicle. It's liquid hydrogen is the fuel, right? You're not burning it, you're just expanding it, heating and expanding. It is a big vehicle, but the idea was that it's feasible, right? So that's the exciting part about this. Okay, so now let's go. We've got a real design, we've got the propulsion models. Can we build a flight simulator? Now, why am I doing? Okay, there is this one evil side in me, which is an entrepreneur. It's not as evil because if I was more evil, I'd be more successful. But it's still, you know, they're still there. And it says, okay, anything and everything I do has to have an economic model, right? So what kind of economic model can I do with the capabilities and the resources I have so I can build something that could actually be useful? And the answer was that, look, if we build a fully synthetic model, we can train the vehicle's autonomous guidance system with a pilot, as if just like a self-driving car, right? So when you have a self-driving car, you have synthetic environments that you drive around in, you get all kinds of data, all kinds of conditions. We can do the same thing with a pilot. So this is just like a little use case. So what we're really up to is we're building kind of like a virtual mission control, virtual, and this is the real thing, by the way. It's a really exciting company in Australia that's built this cube. And, you know, and I'm talking to them, we're going to put our simulator inside there, put an astronaut inside there, have them fly it, and then have all these random conditions so you can build more and more data that's physically based for your training data. So you don't have an IM1, IM2 failures. And every time you have those failures, you know, you're looking what, a minimum of what, $200 million? every time you have a failure or a run, you see all these young guys clapping and they're running exciting, like, hey, we just blew $100 million. Well, this is great for SpaceX, but there's a lot of other companies like the one that sponsored there that who knows? I'm rooting for them really big time. But do they have 1.6 billion in operational budget? Like a lot of them probably blow another 800 million. Every time they launch these things, it's 100 million, 90 to 100 million dollars. And it's awesome that they're being able to learn rapidly. The problem is it's too freaking costly. So we got to do more things synthetically at higher fidelity. Higher fidelity means massively more compute. And that's kind of where I'm up to. It's like, how do we build this higher fidelity, higher quality data that we can then feed into AI inferencing to do guidance, navigation, and control. So we're actually trying to do that. Oops, sorry. So this is the architecture we're actually moving towards for the simulator. Right now we have a prototype, we have a have a workstation, and then and I have to thank my the guys that I'm working with at AMD, Michael Katz, Robert Graham, and Patrick and Charlotte, because they're the ones that are giving me all this hardware. So this laptop's from Michael Katz, my workstation is from Patrick, and so all of the stuff that we're doing, well, I mean, I'm really good at hustling and getting stuff for free. So the idea is that we're trying to literally implement all this, right? And this stuff is expensive, but we're kind of pulling it off. And then what we're doing is we're taking all these different libraries from NASA and then some other libraries that aren't NASA, like Basilisk, integrating them into our environment. So what we essentially have is a full software model. I guess I like to call them parametric virtual models because I came up with those ideas in '93. Nowadays, they call them digital twins, and all they do is do rigid body graphics and dynamics. They don't think about every aspect of the vehicle. So I think parametric virtual models are better than digital twins. But this is an environment that we're kind of doing this is like a simulation side, but there's also a construction side. And that's coming. So to give you an example of something that we did in the last paper, we built a whole parametric procedural pipeline for building rocket engines, right? So we can actually calibrate this thing, and that's exactly what we're doing, to get a Raptor-like engine for a methane LOX engine that we have in MARV. So we essentially start with a set of parameters. We generate a cross-section, revolve it, get the nozzle, and now we have all of the output values for that. And this software model will run in real time. It's a very simple one. Now, in my last paper, we also did CFD analysis, all procedurally, right? So this gives you a first order. If you want higher fidelity, obviously it's going to take more compute. But there's a mechanism that we do in simulations called response surfaces. So you can do a series of simulations at higher fidelity, build response surfaces, and then use those. The difference between training and inferencing is all based on, essentially statistics, right? Well, what happens when you go outside the bounds of training data? You're a host. Now, NVIDIA is making like what? A couple $1 trillion, and everybody's excited by AI. And I'm like, going, guys, AI is great if you know the bounds of the training data. You go outside of the bounds, it's garbage. And we don't even think about that enough. Simulations are deterministic. If we know that our model, our physical model, we can get pretty good numbers. Now, there's problems in physical simulations like turbulence. So when you're doing entry, descent, and landing, you have to get your turbulence right. But there are ways of doing that where you go back and forth between a really high fidelity model that takes an exascale supercomputer, you build a response surface, and then you do a lower fidelity model. So these things, you need massive amounts of compute. That's what Polymath is all about. So the next up, I feel very embarrassed because I tried really hard to get the flight software part in it because it's a flight software workshop. We couldn't pull it off there, but we're gonna get again for SSIB. It's a great conference. I went there last year, and it's only 30 days from now. So we're trying to see if we can get some of the next steps, which is to get we already have the physical models. We can integrate that in for the engines, the different kind of engines that we have. But what we want to do is definitely make the trajectory accurate. That's one tough thing. The stretch goal, which we really are shooting for, is to integrate the sensor actuator model in NOS 3 and Boslick. Inside, we've got some of that software running, but we don't have that. And there's a guy in here, he's in here somewhere. If he helps me out, then we'll have the guidance, navigation, and control algorithm. We'll integrate it together, and then we'll be able to dock. So I'm going to show you some docking work that we did. But before I get there, this has been the bulk of my career. Inventing what is LightStor, this hardware platform, looking at dual phase immersion cooling. I can't tell you how much work has gone into that. It's invisible for this presentation, but it's been an enormous amount of work of my life. So the idea is that this is going to enable, in a very dense system, massive compute simulations. And what we're doing is, here's another thing. I've been around GPUs since they first came out. But the one problem we have when we do GPUs is that when you go sparse, they fail. So LightStor is all about what happens when your memory access patterns are popping around. This is really important because if you run a system with lots of GPUs and you don't utilize them, you're burning power. A lot of people are talking about GPUs in space. If they run any sparse algorithm, they're going to burn power, not get the perf out. This is important to think about that. So really fast, I'm going to show you a video, and then I'm going to actually run the demo live. So probably have a few seconds here left. So I put the video at last on purpose because I wanted to talk about the physics and stuff. But I also wanted you guys to know that there's this stuff that actually runs. So he's going to dock with the gateway. No, actually, he's going to dock with Starship HLS. So you'll see that whole scenario happening. I was hoping to show this live here, and Nick worked all night to try to make that happen, and he managed to get it, but he kept on crashing the demo. So we'll have this a gateway, and the idea is that the simulation for will be based on Trick, and then we'll have the GNC algorithm, because MARV is autonomous, but we're going to have a pilot fly it first, right? So this is the UI for that. Now I just want to. Yes, this all kind of sort of, you'll see I just want you to see one little bit of it. I promise I'll wrap up real quick here. So what's kind of cool is when you come close. Now, as you're watching this, right, what you have to understand is that when you're doing things like, for example, landing on the moon, right, lighting is critical. A lot of people talk about game engines. They don't tell you one thing. Well, if you don't match the physical lighting models, who cares? It's just fancy visuals. We're all engineers. We care about physics. So if we're going to do lighting, we have to simulate the light transport based on the conditions of the moon, right? Well, Unreal can leverage one GPU on a modern GPU. Oh, great. Now we got to build a new freaking renderer. Well, Aclectic's up to the task. So that's what we're doing. Why? Because we need to match the conditions on the moon, number one. And if you're going to run it in parallel, and you're going to do light transport simulation, you're not going to do it in real time. We're going to have like 16 to 32 GPUs in our box. This is why this kind of matters. So in this one, it's using a real-time part of Unreal. But if you're on the moon, right, you gotta simulate the light transport on the moon. And when you start doing light transport, now you're like Weta. Weta does really accurate light simulation, right? But the sure as heck isn't real time. So that's why that stuff is valuable. So you can see it looks pretty good even today, and this was done very fast. So, we got to give Nick a round of applause. He did a phenomenal job really fast. This is one guy, by the way. I have another guy that used to work at Aclectic that works in So, I'm blessed to be really wonderful people. Michael Moore he built the first lander prototype for us. So now this is done. Let's fly the dang thing. Now I'm going to crash it because I'm not a good astronaut yet, but this will be my last part. Can you let me do like a 30-second thing just so I could crash the lander? Okay. We're just going to crash the lander and then that'll be it. So we'll be like, I think this, I love those guys, but we don't want them to crash. That's why we need synthetics. But let me just run this. Oh, there we go. Okay, cool. So let me run we're going to run this thing. So now we can fly it. Anybody, by the way, if anybody wants this, as soon as it's done, just contact me and then you can help test it so it doesn't fail. So this is just gonna run. I mean, if you want to leave, it's okay, because this is just gonna, this is actually, we're gonna fly it. Mhm. Okay. Yeah, okay, so now we can fly this thing. So we have different views we can look at it in. We have the heads-up display. And then, you know, let's crash. We're gonna crash here in a second. Day zero, oh no. See, this is why we need to do it synthetically, so we don't crash.
All right, thank you.
Thank you so much.